there. You alright? Somebody at the back, give me a wave. Yeah, there's somebody. Awesome. Right, if you haven't got a drink, get yourself a drink and start making your way towards the seats or the general standing area. So we're going to kick off the event in just a little minute. So what I'd just like to say, first of all, welcome to the first Toronto KX Meetup. Thank you all for coming out. And yes, little two-second intro about me. I'm Gopala. I'm a KDB Plus engineer at First Derivatives. I'm currently right here working with CPPIB on one of their research teams. So yeah, what I'm going to do is I'm just going to hand it over to Fintan and Quill of KX Systems. So yeah, enjoy.
Thank you very much. Can everybody hear? Yeah. Cool. Can you understand? Okay, my name is Fintan Quill. I'm the Global Head of Sales Engineering at KX. And I'm also joined here by my colleague Abby Gruen over here. We're based out of our New York office, so we're glad to, come to the true land of the free Canada here today. So thank you all for your welcome. And I'll just get started. So we started these meetup groups about a year ago, and I think we have about 48 cities now worldwide. And it's actually exactly a year today when we started up the first New York group, so happy birthday to the meetups. So what I'm going to do is I'm just going to do a short introduction to KDB Plus. So for those of you who know KDB Plus, I'm going to bore you for about 5 to 10 minutes. But I'm just interested in terms of a show of hands. How many people who have actually programmed in KDB Plus before?
KDB Plus or KDB?
Oh, sorry. How many are APL? Or former APL? Cool. How many are here for the free beer? Okay. So I'll get started then. So just a little high-level slide about KX Systems. So we've been in business since 1993. We have offices in North America, Europe, and Asia. So myself and Abby were based in our main sales office in Midtown Manhattan. We're headquartered out of Palo Alto in California. We have a pretty large user community, and obviously we have a pretty large user community in Toronto, which is almost feels like a spiritual home of KX in many ways, with the whole APL community and the Iversonian mindset up here. And in terms of the industries that we work in, we're involved in primarily the financial markets industry, but in recent years we've now expanded into energy/utilities, pharmaceuticals, just general software firms, and also in the telecommunications as well. So we've been primarily in financial services for about 20 plus years now at this point. So what is KDB Plus? At a very, very high level, KDB Plus is an integrated columnar database and programming system. And what we have the ability to do is capture both streaming, real-time, and historical data into one platform. So it's unlike a lot of systems out there where they either do one part or the other part. So we kind of have this Lambda architecture kind of before the phrase became kind of sexy. And the database comes in both a 32-bit and a 64-bit format. And just about 1 year ago now, we made actually the 32-bit version free. So you can download it, run your own apps, build your own net startup off it, etc., etc. And then the 64-bit version is actually licensed. So in terms of some of the features of KDB Plus, it's very, very lightweight, so we can use standard operating systems and hardware. So about 90 to 95% of our customers, I would say, would use Red Hat Enterprise Linux, but we do have a Solaris build, a Mac OS X build, and also, if you're nuts, Windows build as well. And we run on pretty much standard commodity hardware, so anything from a Raspberry Pi all the way up to a supercomputer and everything in between. And we're all about kind of in-database analytics, and what I mean by that is you don't have to unnecessarily copy the data back and forth. So you have a lot of people nowadays who are writing queries, they're extracting data from a SQL database and then they're analyzing it in something like Python or Perl or R. Whereas with us, with the Q programming language, you have a rich analytic tool available to actually work directly on the data. So that helps in many ways. First of all, you have less of a memory footprint and less of a hardware footprint. Second of all, then you've got less of an operational footprint because you only need 1-2 programmers rather than a Python programmer and a SQL programmer. And then also it just saves on your hardware costs as well because you've got much less hardware. And then also you get the really high performance because you're not necessarily copying data back and forth. And we also support compression as well, and we support compression from 3 different viewpoints. We support compression over WebSockets, which I'll discuss a little bit later. So that's if you're having data back and forth to a front-end visualization tool. And we support compression over IPC. So if you have one KDB+ process talking over the wire to another KDB+ process, you can actually, compress that data so you get, better network bandwidth. And then we also do on-disk compression as well. So that can help a lot in terms of saving for your storage costs. So, you might have a petabyte worth of data, and then you can shrink it down to, a good small percentage of that size, depending on how, compressible the data is. And then in terms of parallelism, we support, MapReduce. I mean, obviously the Hadoopsters out there kind of think that they've invented MapReduce, whereas it's just been around for years. And we also have the ability to take advantage of all of the cores on a machine or all of the machines in a cluster. So you can really drive, your machines to 100% as we've done before in many projects that we've been involved in. And we also have a variety of different interfaces. So we have interfaces available for pretty much every programming language out there. So C, C++, Python, Perl, etc., etc. And we also have the WebSockets API that I mentioned earlier. And the nice thing about the WebSockets API now in some of the later versions of KDB+ is that it can work as both a WebSocket client and a WebSocket server. So the WebSocket client then can be really cool if you're doing stuff with like blockchain or Bitcoin and stuff like that, because that's kind of like the de facto protocol for those systems nowadays, so that's pretty cool. So then, obviously on top of KDB+, then we have the Q programming language, which is Arthur Whitney's brainchild. And these are some of the features of the Q programming language. So first of all, it's interpreted. So you can just type it directly at the console, you get the results back straight away. So it's instantaneous results, which results in a lot more productivity and a lot better debugging, etc. And we also are a functional programming language as well, so much like many other programming languages out there, you can create your own user-defined functions, or you can use the custom functions built into the Q language, so you can become very productive straight away. And obviously, harkening back to the APL days, we are indeed an array and vector programming language, which means you effectively don't really have to write loops, so loops go away. So there's a famous website out there, nsl.com, from Stephen Apter, which the NSL means no stinking loops. So that's one of my favorite websites, just for the name alone. And it's also a query language, so you can type SQL-like queries, and then you can intersperse the query aspect with the functional aspect, so you can get very powerful analytics straight out of the box. And one of the nice things we also have that really differentiates us from a lot of other databases out there is a time series aspect. So unlike a lot of SQL databases where they store dates and times as strings a lot of the time, where it's really hard to do manipulation, KDB+ has multiple different time series data types. So these are first-class data types. So it means then you can cast back and forth between these data types and do really meaningful analytics and aggregations and rollups. And we support very low level timestamps down to nanosecond timestamping and millisecond timestamping, month, minute, day, etc. So you can really do rollups and aggregations exceptionally fast and very granular. So this is just a sample of Q-query. So for those of you familiar with SQL, this isn't really too much of a jump. So we're just trying to show here, how easy it can be to do. So as you can see here, we're just doing a select open, which is going to be defined as the first price. So this would obviously in SQL be first price as open. So there's minor syntax change, but to most programmers this should be pretty logical what it actually is doing here. And then obviously we're doing it for the date in question, and then the symbol equals backtick AAPL. So the backtick is just the symbol data type in the Q language as opposed to string or varchar in other languages. And then this example here is actually a comparison between Q versus SQL. So this is where you can see kind of where it veers away from standard SQL. So we can do aggregations, and by definition Q data is going to be ordered. And so Arthur just said, well, why are we saying color 3 times in this query when we only need to say it once? Because by doing the by here, we're already doing the order and the group by, so why say it twice? And then we just move it inside the actual select statement. So as you can see, it's a lot terser, it's a lot more compact form, and actually after a while it becomes much more intuitive rather than writing out these 3 lines of SQL. And then, as I mentioned earlier, KDB Plus has parallelization built in, and it effectively comes for free. And it's not like a lot of other programming languages where you have a very heavy, clunky, multi-threading API that almost abstracts away from what you're actually trying to do. You spend 90% of your time writing the multi-threaded code, whereas KDB Plus effectively takes care of that for you. And so in here, in the first example, we're seeing just a single threaded one. So we're just writing some complex function inside these parentheses here, and then we're passing into that a list of 8 items, where we're just passing in 8 large integers. And then literally to parallelize this, all we do is instead of doing each, we just put a P in front of it for parallel each. So this is very powerful. So say if this is running on, say, an 8-core machine, and if we ran this, it would run almost linearly 8 times faster. So effectively, you get parallelism out of the box for nothing. So it's not like a very clunky, heavy, multi-threaded API. So this is a typical sample architecture for a KDB Plus setup. I mean, a lot of you might be familiar with this if you've worked with KDB Plus before, but these kind of, put together some of the different facets that you can do with the KDB Plus system. And so at the top here, you've got your data coming in. So this could be data coming from a market exchange, or from a smart meter, or from some other IoT device, perhaps from a car or something like that. And so the data comes into the events engine, and in the finance world, this is typically called a ticker plant. So the first thing that this ticker plant or event engine does is it actually logs its messages down to disk. So that means then that any of the downstream in-memory processes can then recover all of their data from this transaction log file. And this transaction log file would typically be residing on a very fast local disk, or solid state drive, or DRAM SSD. And the events engine or ticker plant works via pub sub. So the simplest example of a subscriber to the events engine would be the real-time database. And what the real-time database does is it's effectively a fire hose. It says, I want everything, just give me everything you got. So it's kind of a dumb process in many ways. It just takes the data and it just appends, takes the data, appends. So the memory grows as it grows throughout the day, or whatever you have this pre-configured for. This can be configured very easily. Typically in financial markets, what you have is you have this running throughout the trading day. But what else you can do is you can actually do streaming queries. So they can subscribe to the ticker plant and say, I only want to subscribe for trade data for this bucket of stocks that I have in my portfolio, because I don't care about anything else. So then what the streaming query engine will do is it will only get that small subset of the data, but it could be doing very complex analytics on the fly, such as it could be calculating a VWAP or some sort of stock indicator or something like that. So it's slightly less memory intensive compared to the real-time database, which just grows larger and larger, but it's a lot more computation intensive, because obviously it's taking each message by message and doing these calculations. And typically what happens then is that end of day or end of week or whatever the pre-configured interval is, the events engine sends a message to all its downstream subscribers. And in the case of the real-time database, it actually just dumps all of its contents from in-memory down to disk into the historical database process. So typically then, if you're a trader then, for example, all of your hot data from the day will be residing in the real-time database in memory, so you'll get really fast in-memory performance. And then maybe the older data that isn't as critical from a time perspective or latency perspective, will be residing on disk. But one of the nice things about the KDB Plus historical database is it has the advantage of, it can take advantage of the operating system file cache. So that means then, say if we query for yesterday's data, for example, and then we go back and we query it again, it will likely be cached in memory, so then you'll subsequently get in-memory performance. And this is just for free. KDB Plus is very lightweight. It only has one library dependency, and that's on glibc for compression. So it really works directly with the operating system. So as I said earlier, it's a very low footprint. And so I'll finish off now, but I'll just show you a few resource pages, just to get you up to scratch on what you can do if you're pretty new to KDB Plus. And the first page I'll mention is our wiki page, which is code.kx.com. And if you go to that page, you'll see reference material of all of the different functions. you'll see tutorials, and you'll see user-contributed code, and some articles, etc. So it's a very rich resource. There's a lot of information there, so it's well worth going to if you're pretty new, or even if you're an avid Q programmer and you're just thinking, okay, what does that function do again? I forget. And then we also have a community website, which will actually be getting an upgrade in about a week or two, something like that. But it's pretty cool. It's got like blogs, so you got people who are committing code, and then we've got our Twitter feed, and then you can keep up to date of all of the different meetups. So if you're in another city, you can go and check out another KX meetup there. And so there's lots of cool stuff going on there. So that's more of a kind of a happening place for the developers. And then we also have 2 online forums. And we have one online forum on the list box, which is for commercially licensed users, which has about 1,300 plus members. And so if you post a question, you typically get an answer back in minutes. And then we also have a Google group, as you can see here. And the Google group is just publicly available for anybody to use. And that has well over 1,000 members now, and that's growing as the free 32-bit community is kind of coming out, as it were. And then recently, just within the last week, we started a GitHub page. And so we have quite a lot of projects now in GitHub that people have just committed, where they've written just their own tools or their own open source code on top of KDB+. And just even within the last week since we announced it, we got another like 5 or 6 contributions to it. And there's probably another few out there that we don't know about either. So if you know of any, just let us know and we'll add it to this. So there's a lot of cool code there. It's all just free, just download it and you can start playing around with it. So we're trying to promote the community and grow it a lot larger. So there's some really cool stuff there. So if you're starting working on a project, what will we do, how will we architect it? A lot of the code could already be here, so you don't necessarily need to reinvent the wheel. So we're encouraging people to go there and also to contribute as well. And then just a final interesting website, if you're a bit of a hardware nut, is the Stack benchmarks. So for those of you who aren't too familiar with Stack, they're the Securities Technology Analysis Center. They're an independent benchmarking body for the financial technology sector. They're based just outside of Chicago. And what they do is they run a variety of different financial technology benchmarks. And the one which KX are involved in is called the M3, which is for historical tick databases. And the benchmark consists of 17 different analytic tests on databases of different size. So I think it's 1 terabyte, 10 terabytes, and maybe like 100 terabytes, I believe. And these tests are like calculate the VWAP for X number of symbols for Y number of months, or calculate the MBBO from the raw quote data, or write down all of the data for the day to disk. And it's pretty cool because we run against a variety of different hardware setups, so it's very good if you're trying to architect a system from a pure hardware perspective. So you see that we're working with different versions of the Intel chipsets, so like the SSE instruction sets, 2.1, 4.3, how much of X performance can we get, or else if we're using a solid state drive, or if you're using a SAN or a NAS, or just normal spinning Rust. So it's pretty good if you like to get deep down into the weeds, and they're pretty detailed reports, so they're well worth looking into if you're into the hardware side of things, or just the system architecture side of things. Finally then, of course, is for those of you who are pretty new to KDB+, you can go to kx.com and you can actually download the 32-bit version for free. It downloads in just a few seconds. It's just a few hundred kilobytes in size, which is about the same size as the source code as well, ironically enough, for those of you who know Arthur. And I think that's it. So thank you very much, and I forget who the next speaker is. It's not you. So, Darek. So thank you very much, and if you have any questions, myself and Abby will be around all night tonight, and have a good night, and now I'm going to get a beer.
So thank you very much for this opportunity to share with you Quant's perspective on KDB. These days it's a custom, but every single time you have a talk about some financial matters, you have a long paragraph of disclaimers. So, in the spirit of a disclaimer, please have a very close look at this magnificent painting of Salvador Dali. And just be reminded that the perspective I will share with you is very personal and very subjective. So, having done the formalities, let's start and let's meet a quant. A quant is a determined individual, bent on the idea of testing different investments. As you can see, he is armed and he is dangerous. He is armed in different statistical packages: Panda, SAS, MATLAB, Idiot, and many others. He is quite skillful in operating few programming languages: VB, Java, C++, Python, C#. And he's an expert in extracting information from data, and he is ready to go where probably not too many people have gone before. He faces a universe of financial data. Data on stocks, bonds, commodities, financial statements, indices, loans, derivatives, exchange rate, interest rate, infrastructure, cultural investment, and many others. This data is owned, collected, distributed by multiple institutions: stock exchanges, brokers, investment banks, financial companies, and data providers. Some of the companies are big household names. Others are not very well known, rather obscure. There are examples of few companies which are participants in the data universe. This data, let me just move away from here. This data can be accessed through different channels, databases. Whether these are SQL databases or non-SQL databases, it's one very popular channel. The second way that quant can put their hands on the data are FTP sites. These are the places that vendors provide fairly custom format files that can be downloaded on a regular basis. Or a quant can go to a portal where ad hoc data requests can be downloaded in multiple but well-known formats. Finally, working with Excel, you can use Excel add-ins to download the data directly from the vendor server to your workbook. And here we have a dilemma. On one side, we have universe that offers plethora of heterogeneous data of different quality, different consistency. Data which is owned by many different institutions that offer licenses which are very complicated sometimes. Data that you can get from multiple distribution channels, and each of them with its own idiosyncrasies. On the other hand, you have a quant. A quant would like to have homogeneous, consistent data, which is a perfect input to the statistical model. Okay, a solution to this dilemma is to take relevant data and put it into a repository. You can think about this repository as a small bucket. And yes, Excel is very often used as such a repository because it's very convenient for data acquisition. You can read data to Excel from databases through ODBC drivers. You can read the data from files, whether these are XML files, flat files which are delimited or fixed format. Or you can even go and use the Excel add-ins to download data from few vendors. Once you have the data in Excel, you can just visualize how the data looks like. You can use formulas and VBA code to clean it, prepare the beautiful data set that you can finally load to statistical packages, whether it's EDUs or SAS or MATLAB. Each of them has a very good integration with Excel. But there is a problem. Excel has its limits, and the universe is vast. You put too much data to Excel, or you put too many formulas, let's be assured, it will crash. Okay, so not to risk too much of being accused of serious overthinking of this problem, but if the data does not fit to a small bucket, we can use a big bucket. There is really a big bucket of KDB. Right now, a quant can deal with terabytes of data rather than megabytes, and still have a lot of functionality, much more functionality, which is required for data transformation. Once the raw data is loaded to KDB, We have to do something with this data, transform it into ready data for statistical analysis. One would like to have a homogeneous, consistent data. A lot of financial analysis is based on the total return of time series of several assets, and preferably all those total returns are in the same currency. The total return is due to the price change of a particular asset, the cash flow that this asset generates, as well as any FX movements. Welcome, indeed. And the good news is that all of this data transformation can be done within the database without leaving it through a Q code. Conceptually, we can think about data transformation as made of 5 steps. First, we have to assess the data, how good it is. For data quality, the breadth, the depth, consistency. And I'm not talking about sample data, I'm talking about the full set of data, and they come with a chance of 50 to 100 million, and sometimes much more records. You would like to bring all of them, run a bunch of different statistics, and now that's what I have. Once you know how good or bad the data is, you decide to do some cleansing, because it's difficult to work on the bad data. And this cleansing, the older data you have, the much worse quality it is. Fortunately, this data that we receive usually comes with a lot of redundancy. So from different elements, you can calculate the missing element, or you can check how good the calculations are in comparison to the original data. This allows you to provide the reasonable quality data for the next step. The next step, a fairly controversial step, is a data enhancing. You would like to create new data from what you've got. Well, think about what you are going to get from London Stock Exchange. There will be prices of stocks, dividends, splits, and some kind of a corporate action. Well, first thing you have to do is take all those elements and convert them to the total return. And then, because the stocks in London are quoted in British pound and you're a Canadian investor, you have to convert it to Canadian dollar, this total return. And then you have to ask yourself whether you are doing it at the spot rate or you are going to hedge the currency. So you did few things to create the new data, total return. Once you've done it, you save. In some other example is you get the rates, treasury bill rates, 3 months, and you would like to convert them into total return to know how much you would have made should you reinvest into 3-month TV contracts. The next step is describing the data. And the description can be as primitive as a catalog, or as complicated as a metadata that is capable of running the code, both the code for data transformation and code for data access. In each of those two cases, or any case between, the description of the data itself can reside in the KDB, so you have one place where you have your raw data, your rules how you want to process the data, as well as the final data. And finally, even more controversial step. You want to denormalize the data. Yes, introduce a lot of redundancy. Because your data access will be much easier and will be much faster. Faster, maybe I'll be challenged on it, but in terms of ease of access, it's pretty easier. And once you apply all those steps, you can clearly see how the raw data is being transformed to a perfect set of ready data. Like pure magic, pure magic. Here's the example of ready data, kind of a stylized example, to provide an idea, and to give an idea. The first column contains data. The second is a company, and the third one is a price in local currency. Up to now, the table is totally normal. There is no redundancy. As a part of the enhancement process, we calculate, and this is a data. These are the data for a few selected companies, Canadian and American. During the enhancement process, we calculate prices in Canadian dollar and in US dollar. And we're introducing a little bit of redundancy because obviously the price of Canadian bond in local currency and the price of Canadian bond in Canadian dollar will be the same. But it's okay. The storage is cheap, it's much easier for us to access the data. The last two columns have a lot of redundancy in them. I keep repeating that Bank of Montreal is being priced in Canadian dollar many times, every day as a matter of fact. And I keep repeating that Bank of Montreal belongs to industry banks rather than capturing only once. So definitely, This data is not normal. The columns from 4 to 8 make it 30. The normalized. The reason why we do it is for the access facility, ease of access, and speed of access. Here's an example of data access. All those 3 examples, as a matter of fact, provide a daily calculation of returns for Canadian banks. In local currency, the first query, in the Canadian currency, in the US currency. The results are very nicely organized in a very convenient format. You can very easily compare them. Different columns correspond to the daily returns of different banks. You can draw very easily, for example in Excel, would be a perfect input for a graph. Or you can very easily load it to statistical packages which look at the data in the matrix format. So it's perfect format. Selection criteria are trivial. There is no join to any table. The only condition is provided is some value of a column, that the company, that the industry is equal banks. You might not see it from a distance, but there is a single condition. Thus, calculation of return in the local currency or in the US currency or Canadian currency are exactly the same, because with this enhancement process, we just recalculated some data. So this redundancy pays off significantly in terms of a data access, which is much easier if you are trying to have a normalized data. So here is a happy quant who finally got the data. That was the beginning of this plan. Conclusions. I think it's a very good fit between KDB and quants, because you can deal with a large volume of data, terabytes, and you have a functionality that allows you to transform raw data to the ready data in a very efficient fashion. I think it can be even better. And I have those 3 wishes. So wish number 1, better integration with standard quant tools. It would be fascinating if it was provided out of the box. A VBA integration with KDB, so I can read the data to my VB code from KDB directly, not asking a friendly IT person to write a very complicated C# add-in to support in the environment. Or to read the same data to MATLAB. That would be spectacular. The second wish, more utilities. You know what? I have a file, I would like to load it to the database. Yes, it would be handy to have a kind of a tool that allows me to load it. And save this table, display table, as a partition table. And walk me through this process. To be able to download the data in the format that I can load to another database. It would be even better. I fully understand that somebody who is a very technically savvy and is really a good C# developer and Q developer will be able to write those utilities and will not be complaining about it. But realize that lack of such utilities, ready prepackaged, create an extra entry barrier for a quant. A little hesitation whether it is the right technology to use. And the final wish, which I might be even lucky to have it satisfied, because I told one of the people here who said that's what they do. Better editor. Maybe even integrated development environment that helps a little bit of writing the code and debugging, and maybe even can produce the documentation. So it's easier to maintain the solution that we are putting in place. So those 3 wishes, maybe some naive, maybe some more realistic, conclude my presentation, and thank you very much for your attention.
My name is Leslie Goldsmith, and I'm with Affinity Systems. I've been a software developer for a long time, starting with APL many years ago, like some of the people in this room, and much more recently in 2013 getting involved with KDB+, working with projects related to the smart meter industry and utilities in general. And very recently, Affinity Systems was acquired by First Derivative, so we are now proud members of the FD group. When I got here earlier, actually, I was thinking the great thing about this venue is nobody's going to be able to hear us, which is really good. And then nobody will care either with this great bar here. And unfortunately, I managed to cure at least one of those problems. So I thought I'd begin tonight by talking about why you might want to profile an application in the queue. My talk tonight is about profiling, but I thought I would just motivate why that's important. And I guess I could summarize it by saying perhaps that slow software sucks, which it does, but maybe it'd be more helpful to suggest that there's an important correlation between application performance and software success. These two are often linked together. Software that's responsive is generally more respected by its users, and it's usually perceived to be a time saver. And on the other hand, if you are working with a software application that's not responsive, that performs sluggishly, studies have shown that users tend to disengage, and they actually reduce the rate with which they respond to the application. So it slows down at both ends. So basically, the reason we profile an application is to gain an understanding of how it's working, to understand what it's doing and how it's spending its time, and use that information to help motivate, help inform decisions about how to optimize performance. At Affinity, we find that almost every application that we write has some kind of performance requirement, whether it's the need to generate a web page within some contracted period of time, or perhaps to execute and evaluate millions of events a second. Our philosophy is that software efficiency, like security considerations, really need to be considered at the forefront of the design phase of a project. And you need to have that pervade every aspect of the implementation right through to the completion of the project. Because if you don't do that, if you ignore performance constraints, you can end up building up an incredible technical debt that can take an embarrassingly long time to remediate at the end of the project, and may even require you to do significant software re-engineering. But even if you're careful about the way you write your code, it's important to be able to verify that the software is performing as you expect from an execution perspective. And it's also important, if you chose to play with fire and ignore performance, to be able to zoom in on areas that require attention. So for both of these reasons, both to verify performance and to find the hotspots in an application, it's useful to have a profile as a tool at your disposal. From the show of hands earlier, most of the people in this room had some experience with Q, so you're going to be familiar with its intrinsic execution timing capabilities, which are \t and \ts. And these mechanisms basically provide a way to do micro-benchmarking of an application, such as you might do when you're, for example, trying to determine which of two competing expressions is preferable as you're building up a more complicated algorithm. Micro-benchmarking is really useful for looking at the performance characteristics of small sections of code, but often with synthetic approximations for things like input characteristics, timing conditions, and external events. Profiling, on the other hand, lets you take a step back and get a big picture of how an application is performing. By profiling it, you can get a sense of how the entire system is working, or at least how a representative subset of it is performing. And in that sense, get a macro perspective of where your execution time is going. But both micro-benchmarking and profiling have difficulties. It used to be possible to look at a piece of code, reason about how it was going to be performing, and be pretty accurate if you were to measure its performance. But that simplistic approach to doing execution analysis really doesn't work anymore. And the reason for that is because of the incredible number of abstraction layers that sit between the code you write and the actual impact that that code induces on the entire hardware and software platform. So to see what I mean, here for example is a picture of a microprocessor architecture block diagram. The code we write in a high-level language, or even in language like Q, which itself is compiled, and then the code we write is interpreted, ultimately gets stored as low-level machine instructions. And the way that microprocessor architecture works is it fetches one instruction from memory, it decodes the instruction, it executes it in an arithmetic logic unit, and then the effects of that instruction cause changes to the CPU state and to registers and any memory addresses that need to be updated or modified. The only problem with this description is it's totally wrong. This is the way things used to work about 30 years ago. But nowadays, microprocessors are way more complicated than this. And the kind of machine that you would have in your notebook or your desktop or even in a server would be much more likely to look something like this. This is the microarchitecture of an Intel P6, which is pretty comparable to a state-of-the-art processor from AMD or from Intel. And it's got all the same components as the previous diagram did, but obviously a lot more. But aside from its obvious complexity compared to the way things used to be, there are a few words up here that should raise red flags to you. Words like cache, for example, which give the architecture the opportunity to make copies of data, programs, instructions, etc. in locations for its own convenience in order to improve performance. And that's a great thing. Some of these caches are very large, many, many megabytes. But the problem is it becomes difficult to predict where your code or where the data actually is, and thereby predict how it's going to perform. Other words like reorder, speculative, prediction. There's a myriad of stuff going on here. Modern microprocessors predict the execution path of your program based on what it's done recently. And you might think that having predicted the path, it's going to execute the instructions in the order in which they were written. That's not the case either. In fact, instructions are reordered for convenience of the processor to avoid CPU stalls. So the real order in which they get executed is going to be dependent on data relationships and also on instantaneous resource availability. And this whole picture really applies to just one core, but modern microprocessors have many cores, and often multiple chips. So there are signaling issues between the cores of a chip, between the cores of a processor, and across the processors that you have to take care of. So while it's not fair to say that execution is non-deterministic, it certainly is fair to recognize that it's opaque due to the anisotropic nature of so many of these fancy hardware architectural enhancements that have been made over the years. So however, even ignoring the hardware side of things, there's a lot going on the software side as well. As programmers, we actually owe somewhat of a debt of gratitude to the things we don't have to worry about in a high-level language. For example, if in Q, if we wanted to do a lookup in a table, we don't have to worry about how to implement that search. We can just depend on the fact that underneath the covers, Q is going to make some pretty intelligent decisions about which algorithm is most appropriate for it to use. And that decision will be made on things like the size of the data that we present, the data type of the arguments, and even spatial distribution of the data, and even the amount of free space available in the workspace, which Q may use for its convenience to create temporary data structures to optimize the search. So what I'd like to do actually is to give you an example show you an example of what I mean here. In a Q session, I'll do a simple micro benchmark, timing an expression 100 times, and I will do a lookup of an array within itself, and I'll make the array be 100,000 long, 100,000 long, and I'll take numbers 1, 2, and 90,000. And I'll do the search, and I'm getting two numbers back from TS. The first number is the number of milliseconds that this entire expression, 100 executions of it takes, and the second number is the amount of space that it took. So it's looking like it's taking about 140 milliseconds to do this, and it's taking 2 megabytes. But now, if I make one change to that line and multiply the last number by 10, you can see that now the CPU time has gone up by a factor of 6.5 or something, and the storage required has gone up by 2.5. So what's happened here is Q previously was looking at the density of the data and choosing a direct table lookup in order to do the search. Now, with the spread being much wider, it's picking a different data structure, probably a hash table or something like that. So while \TX provides a great way to do these kinds of micro benchmarks, it isn't really good for taking that step back and getting the big picture. And that's why we decided to take a look at building a profiling tool in Q. Now classically, when we think about profiling, there are basically three different ways you can collect the data. And there's a relationship between the way the data is collected and its impact on the processor, the accuracy of the data, and the amount of detail that we get from it. At one end of the spectrum, we can collect data by sampling. And the way that works is that you have an asynchronous timer that goes off every 100 microseconds or something, and it samples the processor's execution average and uses that as a proxy for what the machine's doing. Unfortunately, this sort of approach isn't going to work with an interpretive environment at all, so we can't use it in Q. The next type of profiling is a function level profiling, where we keep track of the entry and exits of functions, but without attribution of the CPU consumed within the function to the lines of that function. And the third type of profiling is line level, where we also keep track of the function entry and exit points. And in addition to that, we keep track of the boundary conditions between lines, and in that way we can track the CPU to the actual line on which it occurred. which occur. Line level profiling stands the chance of having the most impact on the CPU, and it can really bring the machine to its knees if it isn't properly done. In fact, at Affinity, we've had experience profiling applications that were in Java or C++, pretty active financial applications, and doing line-level profiles with tools that are out there brought the application to its knees, and we had to use a different approach. When we set out to build our profiler for Q, we had three basic goals. The first is we were looking for something that would be easy to use. Easy to enable profiling, easy to disable it, and easy to do that in development context or production context. The second is we were really interested in profiling at the most detailed level we could, line level. And we wanted to be sure that we were incurring the lowest overhead possible. And finally, we wanted to produce something that was able to give us detailed reporting from which we could get actionable insights on how to improve the application. So what I'd like to do now is show you some examples of profiling in action. And I'll start with this pretty simple file, which is a pretty standard way to create a trade table. And in this particular case, the trade table is configured to consist of about 5 million trades taken from 1,000 unique symbols. So I'm going to load this file and execute each of its lines in Q. And we can see right here that something's certainly not going very well because that took an awfully long time to run. Even without profiling though, because of the simplistic way this file is written, each line being self-contained, I could actually use \TS to time every line. So let's do that actually. I'll go ahead and prefix every line with \TS and then run. Oops. Or not. Sorry. Fix this. Apologies, it doesn't help that that is off my screen. Right, okay. This is going to take about the same length of time as it did to load the file, but I'll get a pair of numbers for each line, and those numbers will be just like the TS I did earlier. They'll be the CPU time consumed by the line and the amount of memory that it takes. So looking down here, you can see line 10 is consuming somewhat under 7,000 milliseconds, and that's the dominant portion of the time. The last line is consuming about 1/3 of a second, which isn't too bad. So now what I like to do is run this through the profile. And the profile that we designed actually profiles functions. It doesn't profile files. But if I look at this file, it's been written in such a way so that it has redundant semicolons at the end of every line. And so I can actually just string this together with new lines and use that to create a function. So I'll do that. I have to put the adornments around the function. I've got, as I expect, what I had in the file. Now, what I'll do is I'll load the profiler, which is in a file called prof.q. And the profiling functions are a namespace called prof. One of whose functions is called prof, and prof takes as its argument a list of functions or namespaces that are to be profiled. In this case, I'll just profile foo. Having done that, I'll execute foo. This is going to take about 7 seconds as it did before. And then I will run a report displaying what we got. So this report is showing us a few things. For every function that we profiled, which is just the one, it gives us the name of the function, the line number, the first few characters of the statement of the line, the number of times the line was executed, the total CPU time consumed on the line, including its subcalls, and the CPU time consumed on the line excluding its subcalls. So we can see from this that line 9, origin 0 of foo, so the 10th line of what we were looking at before, has been executed once, but is consuming almost all the time, 6,800 milliseconds, which is very comparable to what we got before. So let's take a look now at what this is doing. This is the line in question. And what it's trying to do actually is be a little bit intelligent about creating the prices at which trades occur. By instead of picking a random price for each of the 5 million trades, it picks a base price for each of the 1,000 symbols and then randomizes the trade price based on the base. But the problem is it's actually doing work that is too proportional to the 5 million symbols. And that's unnecessary. What we can do instead of calling this code here on one symbol at a time 5 million times, we could actually rewrite it as follows. We can do a lookup in PS, and again, we'll do a lookup of the in the unique symbols against the same symbols that we would have created in the previous line, which is 5 million random symbols taken from the uniques, and we will add to that 5 million random numbers from 0 to 1. So this should be functionally equivalent to what we had. I'll save that file, go back over here, and I'll repeat the expression that computes the function foo. And I'll repeat the profile call to foo. And I'll repeat the run of foo. That ran a lot faster. And I'll repeat the report. And so now what we see is line 13, the trade insert line, is the one that's dominating, taking about 1/3 of a second. And line 9, that was so dominant before, is just a bit over 150 milliseconds. So that looks a whole lot better. Now, this is a pretty simple example, so I want to show you something a little bit more complicated. We've also written another package that does workspace searching of objects that are resident in memory. So for example, we can search for arbitrary strings within functions. And that package is called wus.q. So I'll load that, and I'll show you that in the package there's a function called funshow. And funshow takes as its first argument a list of namespaces or functions that are to be searched. In this case, I'll search the entire wus namespace. And its second argument is the strings that you're looking for. I'll just look for the string A. And when I do this, unfortunately some of this is scrolled off the top, but what we get is output that shows for each function in which a match occurred. It displays the line and then puts a caret underneath the A on the line. And you'll see A, of course, occurs in each, it occurs in value, and here A occurs as a variable all by itself. We have another function called SEShow, which does the same thing, but it filters its results syntactically. So the only matches that you're going to get are those that relate to variable names A or constants A that are not part of another expression. And when I do this, I get much less output as you would expect. All the A's and each and value are gone, and I just get the references to A's as a variable. So now, let's profile the workspace searching package and see what we get. To do that, I'll profile the entire package, and I'll repeat this search for A that I did earlier. And I'll actually do the same sort of thing, but I'm going to add another string to it. I'll look for A, or the string FN. And here I get some more output. You can see at the very bottom here there are references to FN. This particular line actually has A and FN on it. And then I'll repeat that line syntactically. Okay, so now I've done 3 different runs, and I will now see what I got in the report. So unfortunately, this doesn't all fit on the screen, but one thing you'll see is that it actually still has references to foo from before. So let's get rid of that. I'll do an unprofile of foo and repeat the report. And now I get a little bit more succinct output that's just in relation to the workspace searching stuff. So we can see here at the top of the display is wus.show. Line 0 was called 42 times, and it consumed 195 milliseconds. But actually, almost none of that was in that function. Almost all of it was in called functions. And the next thing is wus.dippy line 5, which consumed 186 milliseconds. So that must be where all the time is going. So let's switch back over to the editor and take a look at the workspace searching routines. There's actually not much to them. We'll scroll down to dippy. And this is line 5 of dippy. This is the one that seems to be using most of the CPU. And It's actually not doing very much. What it's doing is for each line of every function in which there is a match, it's extracting that line and it's adding to it a line of blanks. And it's inserting into the blanks carets in the appropriate positions that will line up with that hits when they're displayed, one on top of another. So there's nothing much here that we can really do to improve it, I think, except for the fact that, note at the very left edge here, we're actually outputting the results. And we might conjecture that maybe the performance issue is actually coming from the console. So let's delete that. We'll delete the -1 output to standard out. I've saved the file. I'll go back over here. I'll start with a clean slate by unprofiling everything. Now I'll load WUS.Q again. I'll profile the entire namespace. And I will do those 3 searches again, which won't result in any output. So I'll do the A, the fun show with the 2 strings, the SE show with the 2 strings, and then I'll repeat the report. And now what we see is, as before, WUS.show is still being called 42 times, but now it only takes 12 milliseconds. And Dippy line 5 is taking 2 milliseconds. So that clearly is the dominant part of the execution profile of this package. So I think you can get a sense here of how useful profiling can be to help you zoom in on where CPU is going, and in that way give you a good idea of where you should be making changes if you actually have performance problems. But it really is important to emphasize that you have to profile the section of code that's representative of what you're going to see in production. And you have to do it enough times to be sure that the results you get are not dominated by the hardware architectural issues that I mentioned earlier. In closing, I just wanted to say that the software is available on GitHub under Affinity Systems in the Qprop package, and there is a link to it on the KX Systems GitHub page that Fintan mentioned earlier. If you do use it and you have any feedback, we'd really love to hear it because we're very anxious to continue to maintain and improve this for all users. Thank you.